Hello, welcome to the course Electronic System Design. Last lecture we started the software KiCad, where we saw how to install this KiCad, which is a freely available software and which is very powerful software. You can design any complex PCB using this software and it is freely available. You need not to acquire the license to use this software. In that software, we saw the workflow where we start a project and then we design the schematic. For schematic design, we saw that we have a design rule or electrical rule checker where we want to check the electrical rules, and we have a supporting module which is the symbol editor, because for every device whatever we want to put in the schematic, that need to have a symbol. So if it is already available in the library, we just pick from the library. If it is not available in the library, then we have to create it. So this symbol can be as simple as a square box, just input and the output terminals. So that is the easiest symbol we can prepare, or we can define or we can create a different type of symbol which specifies the functionality. For example, the diode, which is given a symbol, for example a triangular and a vertical line. So we can design any kind of symbol which is just a representation of that device. It has nothing to do with electrical rule check or the functionality of your device. So any particular, for example, sensor we are using, we can create any or any type of symbol. This symbol is just a physical representation of that particular device. It has nothing to do with the functionality or the electrical rules of that particular device. So once we create these symbols, we import that into the schematic, connect them together and run the electrical rule check. If it passes, then we go to the next step, which is the PCB design. So today we are going to discuss that PCB design or the layout design, where we are going to create and we see what are the options available in the software. So let's go to the software and see what are the options available. So last time we stopped at the schematic editor, where we open this particular demo project which is already there in the software, and we saw different types of options available, for example highlighting the net, or we pick the symbol from this library where we click on this and this opens up the library. This is the whole library available to us. We can go to any component. For example, this is the STM32F0330. This is the part name and this is how the symbol look like, and this is the pad or the footprint look like. So all these things are available in the library. So this is the schematic which we have taken from the demo project. Now we go back to our KiCad software and look at the other module. The other module is the symbol editor, which we have already seen. So let's look at again for time being. So the other module is the symbol editor, where we create all these symbols for all the components available. We double click on it and the symbol will appear. So we can edit the symbol just by double clicking it, and we can do anything in this symbol to suit our requirement. So this is the symbol editor. Sometimes we use it when we have new kind of device for us. These are the options where we can change from inch to miles to mil to millimeters. So preferably in the PCB design, we measure all the dimensions in mil, as we have discussed earlier in the lecture, that the dimensions we measure in the PCB is using the mil, not in the millimeters. So mil is the preferred scale where we want to measure. The next option is the PCB editor, which is again very important module in the KiCad software. We click on this PCB editor, or we can directly click here. This is the file is already created by KiCad. So we click on this PCB editor or simply here. So it is going to load our schematic, whatever is there. The layout is already prepared because this is a demo project right now we are using. So in that demo project, that is schematic what we have just seen, the PCB associated here is visible here. This is the PCB editor now. Let's go one by one. What are the options generally available in the PCB editor? So the very first option is the grid. So grid is in the background we see all these dotted lines which help us placing components together and keeping that away from little bit. Let's say we are putting this dimension from one dot to another, let's say 25 mil. So this is the spacing of 25 mil, and we want two components to be away 50 mil at least. So we put one component on one dot and the other component on two dots away. So this grid helps us in putting things together. So this is the lock on the grid. You can lock the grid. So these are the dimensions. We preferably go for the mils dimensions. Next, on top we have this option which is board setup. This including layers, design rules, all those settings you can edit in this. This is zoom in, where you want to zoom in. So for zoom in and zoom out, it's better to use the mouse, the wheel on the mouse. You point your cursor wherever you want to zoom in and just scroll the mouse wheel. It will zoom in and zoom out. This is the zoom to fit. You click on this and whole PCB will be visible to you. You zoom to it to fit. This is zoom to object. For example, you have only small object there, so you can zoom to fit, and all the components whatever you have on that window will be zoomed to include all the components together. These are again very similar to schematic editor. Flip options, you can flip X and flip Y, or you can rotate clockwise, counterclockwise. The next is the footprint editor. So this is the footprint editor what we did not discuss last time. When we are using a new device in our schematic, that schematic library does not have symbol for that. We created the symbol using symbol editor. Again, symbol editor is just the representation of that particular device. It has nothing to do with the physical appearance or physical dimensions of that device. However, when we draw the layout, we need to exactly know the landing pattern of that device. For example, we are talking about a BGA package, for example. So this will have the array of balls. So we need to know what is the diameter of that particular balls, how many balls we have on that package, what is the spacing in between the two balls, how many rows are there in that particular BGA package or the array of balls, how many rows, how many columns are there, what is the thickness of that ball. So all these parameters we need to know, because we need to create our PCB so that when the PCB is manufactured, we will put the BGA package on that socket, on that PCB, whatever we have created, and it should exactly align with the PCB package. So to do that, we need to have something called footprint. Footprint is the landing pattern of the device package which we are going to put on the PCB. So we click on this footprint editor for time being, and it will open up this layout type of window again. So footprint is also something like a PCB or design or a layout design where we make a footprint for a particular device. For example, let's say we take a SMD capacitor, for example. This is the, for example, this is the capacitor. Anything we can take, we can just double click on it. This will open up the landing pattern or the footprint of this particular capacitor, which is CP_elect this. And now these are the two pads where this capacitor is going to be connected. So the capacitor will have two terminals, one is positive plate, one is negative plate, and this is how the footprint of this particular capacitor look like. Now if our device is unique, we do not have the footprint readily available in the library, then we can choose any of the symbol existing here and we can update that footprint only to suit our requirement. So for example, we have a unique capacitor for which the landing pattern is very different. So first we go to any capacitor which is closely, which is the footprint is very close to what we want. Let's say this is the footprint. Now we can edit this landing pad. For example, my capacitor has different types of positive and negative terminal. Positive terminal is, let's say, smaller one, and the negative terminal or the second terminal is the bigger one, and they are spaced a little far. So I can change these pads like this. It's like paint and brush we do. We can edit anything, we can write anything, any text here for our understanding. We can update this footprint to suit our requirement. So this is a very simple example of two terminals where the capacitor has only two terminal. One is the smaller one, one pin is the bigger one, so we can edit our footprint. These are all the layers which are for our understanding only. This has nothing to do with the electrical connection. However, it's good to have all these information on the PCB for backtracking if there is any problem. So this is one case of two terminal device. We can have even multiple terminal devices or even complicated packages. Let's go to the BGA package. So this BGA package, let's say we go to this BGA package. So this package has multiple columns and multiple rows, and this single dot is nothing but the connection where the ball of BGA package will come here. So all this spacing between these one ball to the other ball, that is very precisely manufactured so that when we put our BGA package here, it should fit with the landing pattern. So this is how these footprints look like. There are many type of footprints available in the in this footprint editor. Whatever is the closest available to the requirement, we can take that and edit that to suit our requirement. So this is how the footprint editor works. In this footprint editor, we have multiple layers. For example, if we look closely, we have this brown color, which is nothing but the pad. These are the pads where the electrical connection is going to be made. So on the right side, if you see the layer and the object, this brown color is Cu. Cu means the copper. This is the copper, and F means the front, or B is the back side. So if the layer, if we have two-sided board, then the front layer is called F and back layer is called by B. So the front copper is this layer. If we turn it off, then this is the other text, which is not electrical connection, but it is there for our understanding what it look like on the PCB. So these are all the layers we use in our PCB. For example, we use silk screen, we use mask, and many other layers we use. So this is how a footprint look like. We can go to any kind of footprint. There are so many footprints available in the library. Whatever is closest match to us, we can take that as a footprint and start designing our own footprint on that. So let's close this footprint down now. So this is the footprint editor, what we just saw. Next we go to the footprint library browser. This is the library of all the footprints available in KiCad software. We click on it and it will show all the footprints which are available. We can take any of the footprint which is required in our design. We can take this footprint directly from library. The next is the 3D viewer. So 3D viewer is something which shows that more or less fabricated, once we fabricate the PCB, how a PCB will look like after the design. So if we have this demo PCB already opened here and we want to see how this PCB will look like when we put all the components together, or we call the PCB assembly. So from this PCB, if we want to see how the PCB assembly will look like, we can click on this 3D viewer and it will generate a approximate view of PCB assembly. So let's click on this. This is how our actual PCB assembly will look like, and we can rotate it to see how it will look like. So for example, this is the VGA port. On the back side there will be connections of multiple components. On the top we have multiple components. For example, here this is resistance array, which is multiple resistance we are using on PCB. These are all the diodes which we will be using. These are the big capacitors we are using. These are some ICs which we are using in our PCB. These are PCB socket. These are IC sockets. The sockets will come here. This is some IC which we are using in our PCB. These are LEDs. This is the transistor, and this is can be a coil or a transformer. So these are all the components which we are going to put on the PCB and make it PCB assembly. So this is just a visual representation or rendering of this PCB, how it look like after the fabrication. So we can guess, we can have an idea how it will look like when we put all the components together. Next option here is the update PCB from schematic. So let's say when we are designing a PCB and we find out that we need certain more functionality or certain other connection we need to make in schematic, and we want to update our schematic, so we can go back into the schematic, change anything is required, then our PCB also need to be updated from that schematic. So this is the option where we can update our PCB based on the schematic change. If there is any change, that will be reflected in the PCB. This is the design rule checker, very similar to our electrical rule checker in schematic. So what is a design rule checker? For example, we have drawn this, for example, this track we have drawn here, and this track just by mistake comes very close to the other track, which is not acceptable sometime, because during manufacturing, because of certain mishandling or the less capability, this track may get shorted to another track. So there are so many design rules which we put in the PCBs to increase the manufacturability. So to find out if there is any design rule checker has failed somewhere or not, we have this option of DRC, or the design rule check. So we simply click on this and run the design rule check on this PCB. So this is the option of run DRC. It will run all the design rules and find out if there is any error or warning. So here we have tick error and warning. So both of the things we need to see on this PCB. So we click on run DRC, it runs, and there are 0 errors. So errors are something which are not acceptable. You need to find out the solution for those errors. However, warnings sometime may be skipped, because for example, warning are something like we are using some text, let's say example 1 is the text, and this is overlapping with certain other text which is example 2 or any other diode or something. So we write some text and those texts are overlapping to each other. So that has nothing to do with the performance of PCB. That is just for our understanding. So that overlap may not cause an error. It will come under the warning. So warnings are sometime acceptable and sometime they are not acceptable. That depends on us. However, the errors are something which should be taken care with very carefully. So these are all the warnings the DRC has generated. You just click on it and it will point to where that warning is coming. For example, this clipped by board edge. The other error is somewhere here. This is highlighted by this arrow. The other error is somewhere here. The warning, the other warning is somewhere here. So you just click on the warning at the layout editor will point to that place where this warning is coming from. So we close this DRC and zoom to fit. So this is our complete PCB, demo PCB. The next option is the switch to schematic editor. So if we click, we go back to the schematic editor. If we want to change anything in the schematic, we go back to schematic editor from here or from the main window of our KiCad software, schematic editor, right from here. This is again the scripting console we will not be using for the automation. On the left, on the right side, we have multiple options here. Now this is the layers, this is the color assigned to that particular layer, and this is the name of that layer. So PCBs are always fabricated in multiple layers, for example from one layer, two layer to multiple layers, and which layer we are using for particular purpose, that layer is shown by different colors so that it's easy to visualize. So here for example the top layer is given the color brown, and the bottom layer, the bottom copper, is given the color blue. So this whole PCB, it look like the bluish, the so much of copper which is there on the bottom layer. If we turn off the bottom layer from here by this I symbol, if we click on it, the bottom layer will disappear. So if we close the bottom layers, we are not seeing now bottom copper, we are just seeing the all other layers. So in all other layer, these are the connections. If we switch off the top layer as well, then these are the intermediate layer or other layers, for example silk screen which is used for other purpose. So we turn on these layers, these are all the layers we can turn on and off to see the PCB. On the bottom we can choose, for example all copper layers means all top and bottom layers will be visible where the electrical connection will be made. This is all layer where we are seeing all layers. Only the inner copper layers we can see by this, or front layers. So these are all the layers we have options to see in the PCB editor. So these are all the options we have in the PCB editor. So when we'll design a sample PCB later on, we will be using all of these options in our PCB design. Let's close this PCB editor for time being and go to the next module. The next module is the footprint editor, which we have already seen in the PCB editor. This footprint editor is used to design the footprint of particular PCB of particular device. For example, we have this capacitor which is SMD capacitor. This is the footprint of that particular capacitor. We have, let's say, this is the pin header. So and these are the associated footprints for that device. Next we go to the Gerber viewer. So the Gerber viewer is the viewer where we see the Gerber file when we generate from the PCB. So Gerber file is just the layer information. In the Gerber file we do not have any information which says that which device is going to be put here. This is only the layout or the layer information which goes to the manufacturer or the fabrication facility. So Gerber viewer is used to see all those files. Once we generate the Gerber file, we will import it and it will look very similar to the layout in the PCB editor. So this is our PCB editor. This Gerber file look very similar to this, except that in the Gerber viewer the things are not editable. If we want to edit any file, we again go back to PCB editor, edit there and generate the Gerber file again. So if we go to the PCB editor, we can generate the Gerber file from file and we go to the fabrication output, because we want to send it for the fabrication, and there is an option of Gerber file. So we just click on this Gerber file and give it a name you can specify the name in this output directory and click on plot. This will generate all the Gerber file for this PCB. The next module is the image converter. So though it is not used very widely, but for example we have an image or a photo of a layer and we want to generate a soft copy of that or the editable layer in the PCB editor. So that we can do in the image converter. We import that image into this software and we convert that to a file. So this is the load source image. So we click on this and select our image file which comes here and then export to a file. We specify the file name and that soft copy of that image as a PCB editable file will be exported to that particular file. So though it is not very widely used, because when we take the image, the resolution of that image actually is not very good compared to what we draw in the PCB editor. So this is the module of PC image converter. Next is the calculator tools. This is again a very important module which is available in the KiCad software. If we take this calculator tool, the window opens something like this. So as the name says, calculator tools, this module or this tool is very handy for doing all the calculations related to our PCB design. So while designing the PCBs, often we need to find out the thickness, the length of the traces, the landing pattern, how much is the resistance, capacitance, and in fact so many things which we are going to see here. All these calculations are very easy to do in calculator tool, otherwise we need to go back again to calculator and solve some equations to generate all those numbers. In calculator tools it is easily done. For example, we click on resistance calculator. Now, for example, in our schematic we want to use a resistance of 100 kilo ohm. So we write 100 kilo ohm. However, if we search on the market, it may be possible that 100 kilo ohm resistance is not available. Either 101 kilo ohm is available, or 99 kilo ohm is available, or 47 kilo ohm, or there are only discrete values of resistances which are fabricated. It's not like in the market you can find any value of resistance. So let's say I want to use 100 kilo ohm, but this is not available. So it does not mean that I cannot use 100 kilo ohm in our design. It is possible, but this 100 kilo ohm I need to make using series parallel combination of whatever is available in the market. So that I want to generate, which is easy to do using this calculator tool. I write the required resistance. For example, I want 100 kilo ohm resistance. I want to put 100 kilo ohm in schematic. How do I get it? So I click on calculate. It shows me the simple solution is use 33 kilo ohm and 68 kilo ohm. Because this 33 kilo ohm resistance is already available in the market and 68 kilo ohm resistance is also available in the market, I just use these two values, join them in series. So this is how I can get a 100 kilo ohm resistance in my schematic. However, this 100 kilo ohm may not be available as a standard resistance. So let's instead of 100 kilo ohm, let's take some very different type of value. Let's say 139 kilo ohm. So this 139 kilo ohm resistance may not be available, but how do I make 139 on board? So I hit on this calculate, and this shows me that there are two resistances. I can combine 68 kilo ohm and 68 kilo ohm. I can get one solution which is giving me 139 kilo ohm. I can use it to calculate any value of resistance. For example, 131, I can make it using 150 kilo ohm resistance and 1 mega ohm resistance in parallel. It will give me this resistance. So it's very easy to use, and we need to know upfront while designing the PCB, because for example I am using a 131 kilo ohm resistance in my PCB. Accordingly, I put only one footprint of resistance 131 kilo ohm. However, later I come to know that 131 kilo ohm is not available in the market. That time it's not possible to change the PCB. So this information comes handy when I want to use 131 kilo ohm. I know that I need to have two resistances, one 150 kilo ohm and one of 1 mega ohm, that should be connected in parallel. So I will design my PCB accordingly so that it has two footprint instead of one footprint. It should have two footprint, one for 150 and one for 1 mega. And what should be the footprint for this? That I can find out in the library, the footprint library. For 150 kilo ohm what is the footprint, and for 1 mega ohm what is the footprint, and connect them so that they are in parallel. So this is a very handy tool for doing all these calculations. This increases the manufacturability of our PCB. The next option is power, current and isolations. For example, electrical isolation. So when we come to this electrical isolation, we can change the unit of this. So this says how much should be the isolation between internal conductors, what should be the separation or the isolation between the external conductors uncoated sea level to 3050 m. So these are B1, B2, B3, these are the name of these layers. And if our design is 0 to 15 volt only, if I am making a schematic, a circuit which is using only low voltages less than 15 volt, what should be the minimum isolation in the internal conductors B1. So for B1, if I am using less than 15 millivolt, this should be 0.05 millimeter. However, if we want to change it to mil, I click mil, then between internal conductors, if my design is only 10 volt or 15 volt, less than 15 volt, the isolation is 1.96 mil I need to keep. However, if my working voltage is very high, let's say I am using up to 500 volt of voltage on the conductor, then the isolation or the distance between these two internal conductors should be increased to 9.8 mils compared to 1.96 mils for low voltage signal. So as the voltage increases, it means I should have more isolation between these tracks so that there is no interference or the burnout of the tracks because of dielectric breakdown. So from this electrical isolation, I can find out the spacing which I need to put during PCB design. So while PCB designing, I need to figure out the optimum spacing and draw our traces according to these constraints. Then we come to via size. So vias are the way where the signal goes from one layer to the other layer. So all these dimensions we can change using these parameters. We can change the VR dimensions, and we can see the impact on the result. For example, the resistance of this VR, how much will be the resistance if I am using finished hole diameter of 0.4 and plating thickness of 0.035, VR length is 1.6. for example, let's say we want to double this length, then we see the resistance is immediately changed to a higher value. So the resistance of this VR will increase. So depending upon these parameters, whatever we want to design a VR, we can immediately know what will be the impact on the electrical performance. For example, the resistance will increase or decrease, the voltage drop will increase or decrease, how much will be the power loss of the VR, thermal resistance, capacitance, rise time degradation, all these inductance and reactances. So all these electrical parameters I can immediately find out by changing my VR parameters here in this calculator tool. The next is the track width. So when I am drawing the track from one device to another one, I need to find out what is the track width and track thickness I should put if my current capacity is 1 amp. So this is the current, which is the current capacity in ampere. If I want to draw a trace which should carry only 1 amp current, then this is the track width and track thickness. Suppose in another design I want to have a capability of 5 amp. If I change it to 5, immediately my track width and thickness will change accordingly. So for drawing a track on the PCB which can handle 5 amp of current, now the trace width should be 2.76 millimeter and the trace thickness should be 35 micrometer. That I can convert to mil, so it comes out to be approximately 109 mils. So this is how I can decide my trace width based on how much current I want to carry in that particular trace. The next is fusing current. Fusing current is the burnout current, which is the maximum current, but for a very short time we want to put that much current. So that I can calculate from this. So there I need to put the ambient temperature, which is the room temperature, melting point of that particular metal where the material used for traces, and then I can calculate all these values. These are the cable size, so these are the wire properties. The next we go to the high speed designs. These are very handy now, because now for the very high speed designs like 1 gigahertz and above, we need to know multiple parameters. For example, for 1 gigahertz, the wavelength in vacuum is 29.9 centimeter. How much is the wavelength in medium? And the medium is defined by our epsilon r. So for 1 gigahertz, wavelength in medium is 14 centimeter. If I change my epsilon r of my material to, let's say, 2, then my wavelength is going to change to, let's say, 21.19 centimeter. So this is how I can calculate these values. These are very useful for the RF system design. So here now we have two modules which are very important. One is the RF attenuator. So this is the type of attenuator I can use. Based on the attenuation, I can calculate directly what is the values of R1, R2, R3. So for example, I am using a pi attenuator, and attenuation I want is, let's say, 8 dB. input impedance should be 50 ohm, output impedance should be 50 ohm, and I want to calculate the value of R1, R2 and R3. So I hit on the click and this is going to generate the value of R1, R2 and R3. I put these values in the circuit and it will behave like a attenuator of 8 dB, where the input and output impedance will be 50 ohm each. So similarly I can find the attenuator for 4 dB. This is the resistance value. So we have pi attenuator, we have P type of attenuator, bridge T and resistive splitter. We have so many attenuators we can make and find out the values of R1, R2 and R3. The next one is the transmission line. So we have so many types of transmission line available on PCB and silicon substrate as well. So based on the parameters we can know the performance of these transmission line. So the first column here, the first column is transmission line type. We can select any type. For example, this is microstrip line where we have conductor on the top and the ground plane on the bottom. This is the coplanar waveguide where in the same plane we have the signal and the ground plane. This is coplanar waveguide with ground plane. So we have ground on the top as well as on the bottom. This is rectangular waveguide. This is coaxial waveguide, coupled microstrip. This is strip line. This is twisted pair. So these are all the transmission line type. Let's just discuss one for the moment. This microstrip line, now we have two materials to consider. First is the substrate parameter, where this substrate or the FR4 substrate or any other material, what is the property of that substrate material. So epsilon r, for example, for our substrate is 4.5, 10 delta, which is the loss tangent, is 0.02, and all those parameters we put here. Frequency of operation is our 1 gigahertz. Physical parameter, we are putting this width as 0.2 and the length of this microstrip is 50 millimeter, and I want to analyze what will be the performance of this microstrip. So I hit on the analyze. This is going to calculate the characteristic impedance Z0 for this microstrip will be around 67 ohm and the angle is 1.79 radian. So these are the results. Let's say I want to change my width from 0.2 to 0.4 and analyze again. Now my characteristic impedance is 46 ohm and the angle is this. So these calculations are very handy when I design the PCB for RF applications or the transmission line I need to design in the high speed PCBs. The next is the drawing sheet editor, which we rarely use. This is the sheet and the layout we can change by this drawing sheet editor, and these are some plugins. So if we click on this plugins and content, it contains all the plugins which are already available in the KiCad. So we have so many plugins available from the third party vendors. We can import all those plugins to KiCad software and use them. So these are all the modules which we have in the KiCad software, and now we can use any of these to create our PCB in PCB editor. So here we have seen today the workflow of KiCad software. We have multiple modules available in the software like schematic editor, PCB editor, Gerber viewer and calculator tools. These are very important modules. For example, the calculator tool comes out very handy when we are designing the PCB. That time during the design phase itself, we need to find out the thickness of the trace. So that thickness we can calculate from the calculator tool. For that we need to find out first how much is the current capability of that particular trace, what is the maximum voltage of that trace, and what is the frequency of operation of our signal. So once we have a very high voltage trace, it means we need to have the spacing which is defined in the DRC or in the calculator tool. If we have a very high frequency signal 1 gigahertz or above, that time we need to find out what is the characteristic impedance of that trace. It is less than 50 ohm, more than 50 ohm, because we need to match the impedances to this particular trace impedance so that the signal does not bounce at the interface. As we discussed earlier, whenever we have a impedance mismatch, the signal is going to be bounced. So while designing the PCB, we need to find out the characteristic impedance of the trace so that we terminate this trace exactly by that impedance and the signal does not bounce back into the opposite direction. So these are some modules which are available in KiCad, which we are going to use during our PCB design. So that is all for today. Thank you.